No, show that.
So what is it? It must be about 8 o'clock. I'm getting some feedback.
I agree, but this is, I cut my sound. So the problem comes from him.
So I don't know how
I
to
know why, wait.
I don't know how to cut my sound because I don't have that.
And now? Non,
Wait.
ça vient de toi.
Attends, ça vient de ça.
Non, ça vient de toi. Il faut couper ton son.
J'ai coupé mon son.
Mais non, on t'entendrait pas si t'as coupé ton son.
Tu veux dire ça, comme ça?
Bah oui.
D'accord. I'm getting...
Yeah, now it's working. Huh?
I'm gonna make you host, so wait.
And you don't need to make him host.
For this to work.
I think it works.
Okay, can you say hi, please?
No, we won't hear.
Hello,
It's gonna make an equal.
We can't hear him.
But
you can't hear me?
You can hear us, Ken, correct?
I can hear you, yes.
Yeah, but
You
he
can't hear me?
talk.
Yeah, but that's the same problem with that setup. What's filtering out? Are you thinking by making him a host?
Yes.
Okay.
Make you host.
As long as I don't have to touch anything.
Done. So Ken, can you talk?
Yes.
Okay, so the system that solves this doesn't work, right?
No, wait, there may be a volume issue here.
Go ahead.
Talk, Kenny.
Hello?
Yeah, we can hear you.
Okay. Good.
I mean, what else can you do?
So,
Like the powers that be.
Yeah. So whatever they are.
Yes.
okay. Ready?
Yeah, I guess so.
Ready? Okay. So thank you everybody for being here today. So it's a 12th session of PMMC. We're very happy to have Chetan Prakash from California State University today. If I understand well, he's presenting a very a novel way of novel model to explain how you can build reality from phenomenal experience, which is like a dual point of view from the point or the opposite point of view from the one we take usually. So we're very excited to hear about it, and in particular, how you can, by specifying some parts of phenomenal experience, arrive to a common notion of reality, if I understand well. And so I leave him present today, observers and their physical interfaces in conscious agent theory. Thanks a lot for being.
Thank you very much, Grégoire. And thank you for this invitation to all of you. It's a great honor for me, and it's also a pilgrimage, which I'll explain after the presentation is over. Okay, so the title of this presentation is Observers and Their Physical Interfaces in Conscious Agent Theory. And you can see this joint work with a number of people, including Don Hoffman, Robert Prentner, and Shwapan Chattopadhyay. So general overview of the talk is going to be in 4 parts. The first is a review of the interface theory of perception. The second is conscious agent theory. The third is defining observation and its trace logic using conscious agent theory. So within that theory, we're hoping to develop an understanding of what an observer is. And finally, some very speculative comments about a possible physical projection from conscious agent theory. So just to set it up, here's a quote from Steven Pinker in How the Mind Works. He said, "We are organisms, not angels, and our minds are organs, not pipelines to the truth. Our minds evolved by natural selection to solve problems that were life and death matters to our ancestors, not to commune with correctness or validity." So that suggests that we should start understanding perception with an evolutionary theory. Okay, so the first part of this talk is on the interface theory of perception, and that's in distinction to physicalist evolutionary theories. A physicalist evolutionary theory believes that our perceptions have evolved as veridical representations of the objective world. I guess I must have a bias because I forgot the R. Veridical perceptions are the perceptions which are attuned to the structure of the world. So we're assuming that there is a structure of the world that is objective, and our perceptions are attuned to it. In fact, through evolution, they're attuned better and better. That's the physicalist theory. In contradistinction, Don Hoffman came up with the interface evolutionary theory, which says that our perceptions have evolved as a user interface between us and an objective world, which is why the background here is symbolic of a user interface. So interface perceptions are those which are attuned to evolutionary fitness. Okay, so as a result of this point of view, in the interface theory, we think of space-time as akin to our desktop, or if you like, sort of a parameterization of our desktop. Physical objects are then akin to icons, to continue the metaphor. Icons seem to interact via what looks like a physical law, but physical causality itself for icons on a desktop is a fiction. Okay, so it's a fiction, but we take it seriously because it's functional, it's evolutionarily useful to us. We don't take it literally from this point of view of interface theory. So you might ask, if that's the case, why don't you step in front of a train because it's barreling down at you, but it's not real? To which I would answer within this context that my icon should not step in front of the icon of the train because something terrible could happen. What exactly happens might be very different from what I think is happening, but something seriously is going to happen. I mean, if I take that thesis over here and I move it to this icon, something serious could happen. I could lose my thesis. So, we apply evolutionary game theory to this interface theory of perception, and we come up with the following theorem that under natural selection, and assuming that there is an objective world, the probability of veridical perceptions is close to zero. Okay, and I'm just going to run through a whole bunch of theorems which were derived on the basis of the interface theory and evolutionary game theory. And I'm not sure of the variation in background of the audience, so I'll go through some detail.
You can go into detail.
Okay, okay.
Yeah.
So in addition to this basic theorem, which I will repeat later, there are 6 fitness beats truth theorems, as we call them, where we see that interface agents dominate agents seeing the truth of a given objective world. Okay, so we call this the resource game model. This has been simulated, actually. The original work was simulations, and the mathematical work that was subsequent to that justified the simulations too. So there are certain assumptions that we make. The first is that the states of the world form a compact regular Boreal space, typical of most of the things you see in a cognitive science lab. The perceptual space of a given species is a finite set. The world, which I'm calling W, has an a priori probability measure. If we don't know anything else, we assume that it has a uniform or some kind of probability measure, which is at least absolutely continuous with respect to the uniform measure on the world. And as I said before, the structure applies to the majority of situations, at least all the ones I know of. I'm not a cognitive scientist, but it appears that this is a decent assumption to make. And what it does is it allows us to do Bayesian inferences. Okay, so modeling perceptual strategies again is that you have a set of world states W, you have a perceptual space X, and a perceptual strategy then assigns a percept to each world state. So it's simply a function from the world states to the perceptual space. Now, this is an ideal strategy. In fact, most strategies are dispersive. And so in that case, P would become a Markovian kernel, which assigns to each world point W the probability that you get a perception of X. Okay, so that's what a perceptual strategy is. Fitness then is a function which is specific to whichever species you're talking about, the environment that it's in, and its action class. So the same object in the world could have a very different fitness value for a different species. A slab of meat in front of a lion or in front of a rabbit has very different fitness values, and also in terms of its action class. So given these, it assigns to each world state W a positive number, its fitness, and so it's just another function into the positive reals. So there are two kinds of perceptual strategies, the veridical or truth strategies and the interface strategies. A veridical strategy is as follows. It first uses Bayes' theorem to estimate for each possible percept X down below in the perceptual space, a maximum a posteriori world state WX, which is going to be the element W sub X of the fiber over X under the perceptual strategy, maximizing the a posteriori probability from Bayes' formula. And in this context, that's what the formula comes out to. So this is all fairly standard in terms of perceptual strategies. Okay, so once you've done that, once you've found your W sub X above each X, you then choose that percept, which we'll call X sub 0, that maximizes the fitness of its maximum a posteriori state. In other words, you look at all the W sub X's and you look at the one X for which its W sub X has the highest fitness. And that is the standard way of computing the perceptual strategy for a truth situation. Yeah.
You start with you said you had an a priori on the X, right?
On the W.
So you have PW and PX condition on W. So this is how you relate the real world to I mean like the
objective world, if you like, yeah.
So
right.
Okay.
So I'm just looking at an ideal strategy.
Is on what?
A posteriori probability is
It's going to be on the W.
Yeah.
X.
Yeah.
Okay.
Right.
Yeah.
So yeah. Good. Okay. Right. So next we let's look at interface strategies. Okay. So an interface strategy also is a two-step strategy. First, what it does is it computes the average fitness of the fiber over each X of the perceptual map P. So you look at the fiber over X and you just find the average fitness using using a certain formula, which is given as follows. So yeah, the fitness of the percept X is the average fitness of all world states W that could give rise to X via the perceptual strategy P. And so that's also computed using Bayes' rule. It's the average over the fiber P inverse of X is this particular formula, where of course, now you're introducing the fitness directly.
Because, sorry, I have bad memory, but looking at this formula, to me, what I remember was very similar or not identical to the previous one? What's it?
Well, yeah, I think I went over the thing very quickly in the beginning. G is the density with respect to uniform measure.
Yes, but what is different in this perceptual strategy and fitness equation expression from the one that is just direct?
No, your condition. So you're looking at the expectation conditional on X.
Oh, because
Right.
it's the expectation.
Yes,
Yeah,
of
The
F.
conditional was the
And
same, yeah?
before was the arg, you were looking at the maximum a posteriori. So the arg max of a P,
Oops.
P omega knowing X
Sorry.
for each X. Before you had he was looking at you look at the a posteriori and the most likelihood state of the world, and now it's the expected state of the world given the a posteriori for a given perceptual.
Okay. Show the formula now.
So this was this is Bayes' formula. Okay. Now I'm using this.
Show the formula.
Oh, it hasn't. Oh, sorry. I could see it on my screen, but not yours.
Okay.
Sorry. Yeah. So this is the Bayes formula, and if you look at the expectation of the fitness function on the basis of this formula.
I see.
Yeah.
Okay.
So thanks. Yeah. Maybe I should have put that as an extra part of the equation. Okay. And we're almost back to, this is a bit slow, but okay, here we are. All right, so that's how you compute the fitness. And then the second thing you do is to choose the percept x sub 0 that maximizes the average fitness of the fiber. Okay, so this is the formula for the choice of the strategy under interface. Okay, and then the question becomes, now you have two clear strategies. Which strategy dominates? So that's why we bring in evolutionary game theory, where we develop an evolutionary game between the true strategies by computing a payoff matrix for the two strategies. Okay, so payoff matrix tells you what happens when interface comes up against interface or against truth. That's A and B. And what happens to truth if it comes up to interface? What's the payoff to truth when it's played against interface? That's C. And similarly, D is truth versus truth. Okay, so this is fairly standard in game theory. And the basic result is that interface would dominate truth. In other words, it will eventually drive truth to extinction if the payoffs for interface as the first player always exceed those of truth as the first player. In other words, if A is bigger than or equal to C and B is bigger than or equal to D. Okay, so it's a fairly simple and straightforward theory that we're using. There's something called the replicator equation, which is based on the fitnesses for the two different strategies. I won't go into this in too much detail. I think it's fairly standard, if that's okay. And this is what the equation says, and you can apply this equation, and there are various possibilities that will happen.
Just maybe.
Yeah.
Spell a bit this equation.
Sorry,
And others.
this thing moves back very rapidly. Sorry, I'll have to get.
Just give it.
Yeah. Okay. So x sub I is the proportion of species using strategy I, and similarly for x sub t for strategy t. And then the fitness is given by these payoff functions. Okay, where I is the first guy, it'll be AXI plus BXT. And similarly, for when T is the first guy, the fitness will be C, which is the payoff for it going against I, and D, when it's payoff going against T. And then the replicator equation is the equation that shows how X sub I, for example, changes with time, where time is the number of repetitions of the game. Okay, so moving on. This is something I took from Novak's evolutionary dynamics. You can have various possibilities that A dominates B dominates A and B are bistable, or they coexist, or they're neutral. And So we want to examine which of these is likely under the circumstances. Okay, so the first theorem is that fitness beats truth, as we call it. And it says that if you have this world, W, and the finite sensorium X, over all possible fitness functions and a priori probability measures on W, we're sort of averaging over the whole thing, the probability that an interface perceptual strategy will dominate a veridical strategy is given by a bound. It's at least this big. And so the result is where X, the magnitude of X is the size of the perceptual space. So if X is very large, this is a number which is extremely close to 1. And so as the perceptual space gets bigger and bigger, veridical strategies get less likely to survive on the basis of all these assumptions. Okay. So
wait, so I'm a bit confused. So the fitness function is from a compact space to R, and what is the measure that you put? What is the assumption on the measure you put on the fitness functions? Here it's overall. So you say overall possible and a priori measure the probability that an interface perceptual strategy will dominate.
yeah.
This is over a measure on fitness function and probability measures, no? And it's an over a measure on the
Yeah, for an arbitrary prior probability measure. Yeah. So in a sense, it is.
Maybe I didn't understand again. So this is like for given the fitness function, given a probability measure, then the probability of interface.
Right.
Perceptual strategy will dominate.
Mm-hmm.
Yeah, it's at least this. Okay.
Yeah.
So why is it stochastic? The game. I didn't understand the game. In fact, the way that the two agents are playing. So why is it stochastic that the strategy is that one strategy will dominate the other? What makes it the game between the two agents stochastic?
Well,
what is random just?
The fitness functions, for example, there'll be certain fitness functions where the veridical strategy might win.
So yeah, so then my question is, what is the measure you put on the fitness function? Because the fitness function are continuous functions on the complex sets, right? So you have a natural measure to put. So what is the assumption on the measure?
Yeah, so they're actually. We're considering actually the finite situation. We're not considering a general situation, but it could be a very large finite situation.
Yes.
Yeah. Okay. Yeah, it's a good point. I mean, we started off with talking about compact spaces, but really, this theorem takes I should have said over here that this is a finite world. So good point.
Probability measures. So then you assume uniformity on the W.
Yeah. Yes. Definitely. Okay. So let's see. Yes, I need to press this. So that we have certain other structure theorems based on the same assumptions. Again, finiteness in this sense, but again, very large world states compared to the size of the perceptual space, which itself could be very large. Okay. So so these other structure theorems, here let's make we consider the number of elements of W to be n and the number of elements of X to be m, and n is usually much greater than m, and define an admissibility ratio called rho. And we ask the question about among the possible fitness functions from W to X that are homomorphisms of a given structure, what proportion of these homomorphisms actually achieve the maximum fitness value for any given fitness value. Okay. So the first theorem is in this row, which is the second theorem I'm talking about, is the theorem that says interface agents dominate agents that veridically observe total order. So we consider various types of structure. The first structure we're thinking of is total order. And there it turns out that this coefficient rho, which I mentioned over here, which is the admissibility ratio, is given by a certain formula. And if you let n go to infinity, if you let the size of the world go to infinity, or certainly dominate m, then in fact rho goes to 0. So the interface agents in a very large situation will dominate veridical agents again in terms of total order. The vast majority of interface agents will not see total order if it happens to exist in the world. It's lost. That structure is lost. And so going very quickly through some other theorems, the third theorem says that interface agents dominate the veridical agents with permutation group behavior. Again, we can compute the number rho exactly. And again, it turns out to be robust under approximation. Okay, so looking at just some random, or not really random, but some arbitrary types of structure. The next one we wanted to look at was a periodic or cyclic group behavior. Again,
Just a
yes.
question, I'm sorry. It's very
No,
basic,
please.
But so when you compare the version of the veridical model, let's say, versus the interface model, one of the big differences is that in the second case, you have an expectation. So basically, that makes me think about the law of large number, the robustness that you are talking about here by showing us those terms.
Yeah, and this is a different.
It comes basically also from the law of average, things that have to do with central tendencies that we better estimate when you have a large sample. Can you make connection with basic statistical theory, or it's completely independent?
I know, I think that that's a very good point, actually. You mean some kind of law of large numbers behavior?
Expectation.
The expectation does smooth things over. Yeah. And the fact that you are using an expectation, maybe from a mathematical point of view, that's the reason that this thing dominates.
Right. That's what I was wondering.
Right. No, I think that's a good point.
Okay.
Yeah. And it's worth exploring, actually. So cyclic group behavior, again, you do find that there is domination, but now there's an interesting thing that if you do an approximation instead of an exact formulation, then it starts to break down, and so it's not that robust anymore. So there's some structures like the next one, which I will show you here, which is the measurability. Okay, now measurability turns out to also break down if there's an approximation, and so there could be some things that are that veridical inferences can recognize as well as interface agents, but a lot of other structures seem to just disappear. In other words, if we are interface agents, then our view of the world does not necessarily represent the structure of the world as it is. We are seeing structure in the world, or we're losing structure that may actually be in the world. So the implication of this is that our physical vocabulary, as an extension of our perceptual vocabulary, is the wrong vocabulary for this causal structure of the real world. Okay. So you might object. You might say there's a consistent agreement on things like 3D shapes and textures, etc. How can you say that these are fictions on our interface? And just to be very provocative, I would say these are very strong intuitions, but they are dead false if you buy this theoretical development. Very soon I'll talk about a theorem that is a consequence of this and the conscious agent structure, which says that an agent can see spatial or probabilistic properties in the world, whether the world itself actually has them or not. It really is something that is intrinsic to the agent itself. And I've seen that there is some connection with the PCM model there, I think, which is very interesting. Okay, so if evolution favors interfaces as perceptual strategies, and if, for example, space is the construction of a species-dependent mind, this invites us to start out anew in developing a model of consciousness, not a physicalist model, but a different kind of model. Okay, so that brings me to the second part of the talk, which is about conscious agent theory. So let's go over some of the assumptions, or all the assumptions as far as I can tell. The 0th assumption is agents are part of an objective world. The question is, what is that objective world? So assumption 1 is that agents have conscious experiences, or qualia, and the qualia are perceptions of that world. Another way to think about qualia is that they are actions of the world on the agent. These are, two sides of one coin, basically. Assumption 2 is that agents are able to act on the world. And assumption 3 is that based on their perceptions, agents make decisions to act on that world. And in principle, this is where free will come in. But, if we don't know how to describe free will completely, at least from a God's eye perceptive, well, I shouldn't say God's eye, but from the outside perspective, then we'll use probabilistic ways of describing will or belief and so forth. Okay. Assumption 4 is the quantification assumption, which says that experiences, decisions, and actions all have probabilities and probabilistic relations between them. This is a sort of basic assumption that any scientific theory, I think, has to make if we want to be able to use mathematics to describe things accurately. Assumption 5 is sequencing, that for a conscious agent, interactions are sequential. They possess counters. This is not the same thing as physical time. It's just a sense of subsequentness or sequence. Okay, so as a very minimal modeling of conscious agents, we describe a conscious agent as a 7-tuple. Okay, it's consists of these, first of all, of W, which is the world, X, which is the experience space of the agent, G, which is the action space of the agent, okay, and then P, D, and A are all, these are measurable spaces, so we can talk about probabilities. And then P, D, A, and A are Markov kernels that tell you what happens in each direction, okay? So informally, we refer to X as a qualia space. I think Don likes to call it a headset. And G is an action space or a controller. The union of X and G is the agent's interface and may not resemble the outside world at all, okay? The measurable spaces may, of course, have additional structures, such as topological, metric, vector, group structures, and so forth. And then in that case, the kernels would be homomorphisms of these structures. But at this point, we want to be as minimalist as possible. So we're just taking it to be this. Okay. So, so conscious agent theory is, yeah, sorry.
I misconceived M. What is M?
N? Oh, sorry, N is the counter. Yeah, that's just the integer.
Right.
Thanks. I think I may have skipped that. Okay, so ontology is the next assumption, and that brings us into conscious agent theory. This is the thesis of conscious agent theory, which is that the world of a conscious agent is a network of other conscious agents in interaction with one another. So what is this world? We're making the assumption that it's consciousness all the way down. Okay, so this is a consciousness first theory, and in contradistinction to pretty much the standard theories that are in existence here. And the point is that if and when a physicalist theory can actually produce, say, from within it the taste of chocolate, then that would be great. But so far, the world's best minds have not been able to do that over 70 years of effort. And so it behooves us to actually try and look at an alternative foundation base. And that's what we're doing. Okay, so these CAs are in one-to-one interaction with one another. There's nothing other than the network. Individual CAs are nodes of the network, and their potential connections are its directed edges. Directed in the sense that you could have a P coming in and you can have A going out. One CA's action on another CA is perceived by the other CA as its experience. So there's this mutuality that I mentioned before about the world. Okay. So this is what is called an objective idealist theory. I'm not myself a philosopher, but I've been reading about this in various places. I guess in the West, Leibniz, Schelling, and Pauli, Jung were the proponents of such theories. In the East, yoga, Advaita Vedanta have been strong proponents. Of course, there are many other approaches in the East other than these. And one nice little article which covers many of these is by Harold Altmannspacher that I was reading recently. Okay, so what's the dynamics of such a network of agents? Well, first of all, we need to define what is meant by an interaction in the network. And I'm taking that to be simply a subset of nodes that are talking to each other. Talking means that there's an action, there's a perception. We can think of experiences of a CA as preceding their decisions, which subsequently mediate their actions. And so,
just a
oh, sorry.
So this multi-agent setup, you still have your triangle per agent at the representation of the variable and so that means that in that model, do you assume that W is shared by all agents? That's the same W?
W is a collection of other agents. It's a network. So
W itself become a network of agents?
Yes. So there's little triangles all the way down. And in principle, they all have connections. So if you think of just the X and the G and the D between them, as you could call that a reduced agent. So the network is built up of these and connections between them. Yeah.
And that is W, the network?
That is W. Yeah.
Okay, because your ontology is.
The ontology is that there is. Yes.
I'm connecting with that.
Yeah. Thank you.
All right.
May I say something?
Yeah, sure. Please.
So the agent you defined is also a member of W.
Yes.
Yes. Okay. So it's a non-well-founded structure.
Yeah, in fact, I found your talk fascinating at Bamberg. I think, yeah, I think at that you can take 2 points of view, but I think to have a different W for each agent would be even excessively complicated. And so non-well-foundedness is, I think, somehow essential here. And I'd love to talk to you more about that. Okay, so I'll go ahead. All right, so okay, so the interaction structure is going to be something very interesting. You can define it as a subset, as an element of what I'm calling A bar cross B. There probably is a term for this in mathematics that I'm simply not aware of. But it consists of those ordered pairs so that if A is say acting on B, then B is not acting on A at that particular interaction. B is receiving an experience and A is acting on it. So a subsequent interaction could, of course, include an action of B on something else, including the original guy. Okay, so there's an underlying counter and a stochastic process on this set, this partial Cartesian product, such that at each count n, there is under some probabilistic law an interaction. Now, what is that probabilistic law? I don't know. That's something that's happening in the whole world as a whole, okay? And whatever this stochastic process is it's a stochastic network dynamics, which is incredibly complicated. And we really we don't have the God's eye view to describe it.
Do we have to assume that there is a universal counter, or it could be, because that's kind of a synchronic world with some form of clock for synchronizing all those exchanges, but couldn't they be asynchronous? You know, with each has its own counter and deal with it, and one enter into the interaction with another. You know, the clock, the user is running, but it has to wait. And here it seems that what I would call synchronous or universal clock assumption, thinking about computer science, may not be necessary even for you.
It may not be. Yes, this is just a proposal.
The stage,
right?
Because it's elegant, it's clear, but perhaps you could extend it.
Yeah, I definitely thought about asynchronous situations, but I'm trying to set the stage. You know, that we don't have an actual notion of physical time here, and so the question really is, if you have these interactions, can you think of moments, even though you don't have time? Can you think of moments? And in a moment, there are some interactions happening. Okay. No, the counter could be continuous, or it could be discrete.
It's easier to set it
yes.
that way.
It need not even be one-dimensional, for all we know. Yeah. So yeah, I definitely agree. But I'm setting a stage, and then I'm running away from it in the next slide.
Yeah, but it's good that you set the stage in a manner that is factored.
So S.
So we can question it.
So your S for one agent gives the order between the interactions, or the way that you apply the kernels to perception.
No, this S is not the same as the counter of an agent. This S is an underlying counter of the entire network.
And so the counter of the agents corresponds to applying one of the kernel at one time.
Right. Right.
So now they all have this for each agents.
Right, and they're all different counters.
So why do you need this?
Well,
what is the rule of it?
there's some dynamics of interaction, right, going on.
It's a bit
Things
like,
are lighting up.
It's a bit like the clock of your CPU, your S. And then, you know, an agent may intervene at a certain particular time, but it has always to fit into the
Right.
beats of that
So
clock.
is it good to say that S chooses samples an element in IN for each time? Can say this?
Well,
And each time you go from
well, I said under some probabilistic law,
Yeah.
which is parameterized by S.
In terms of time.
It's parameterized by S in terms of time, and there's some law, and I'm not even going. I have no idea what it is.
So at each N, at each like a counter, you choose distribution.
Yeah.
But
Yeah.
you could
And
perfectly,
interactions.
is it possible in your framework that, sorry, it's not by analogy, but your counter S runs at a frequency that is higher than your counter N?
Yes, indeed, indeed it will be. In
It will
fact,
be, in fact,
yeah, it will always be much higher. And this probabilistic law, I haven't given a notation for it, but this probabilistic law could be dependent on the states of each of the conscious agents in the network at that N. I mean, you know, and it could be even dependent on previous states, for all I know. It may not be Markovian. It could be something completely wild.
So it's almost like the counter S is the hardware and counter N's are the software.
Yeah, I guess you could say that.
Analogy you want like it.
No,
Like that to computer science. You can have virtual clocks that are software.
Yeah.
But the clock of your CPU, well, yeah, you can accelerate it, boost it, but normally it has a fixed frequency for a certain amount of time.
Right.
And you have to live within that frequency to run your own internal clock. And of course, the clock of the CPU has to clock faster than
Right.
to tick faster than the
I can see the analogy. It certainly makes sense
To help
because,
me understand.
yeah. So, how much time do we have?
Plenty of time.
Okay,
1
good,
hour.
good. That's great. Thank you. So like I said, who ordered this stochastic process? I don't know. So this is not something that we've actually ever mentioned before, but I thought let's try to think a little bit about the stochastic process on the whole network and realize that it's not really what we are seeing, what any given conscious agent is seeing. What a given conscious agent is seeing is a network, is a dynamics, but on its own X space. Maybe G space too, but I'm just going to concentrate on the X space right now. Okay, so for this agent, if you now pick a particular single agent, you can develop a phenomenological dynamics on this agent in a very simple way. That there's a transition probability which is defined on X, okay, which we're going to call Q, and Q is simply the product of you do D, then you do A, then you do P. This is sort of in the opposite direction. What I'm describing it as D, you've received percept X. That percept X then is decided upon, you make a decision on the basis of that to make an action, to select an action G. You then perform that action G to change the world state, and then you receive from that new world state a new percept X prime. Okay, so this is not the usual mathematical way of writing transition probabilities, but I thought it would be pictorial. Okay.
And why don't you need, couldn't we say, well, you could also have left to your D, another P, but that will refer to the time before, because your X, in your D of X toward J, has to be defined, so it comes from the previous cycle. Right?
Yes,
So here
it does.
you are at a moment.
Yes.
And your moment starts, yeah, because you start from conscious experience, so it starts with the percept.
Yes, you start with a conscious experience, and then you go through this process. And next time you have an experience, that's your next moment.
And
for
we
you.
agree that in this particular setup, action is on another conscious experience. Because you say that in your framework, in this ontology, you only have conscious agents that are connected.
Now, you could conceive of the possibility of the action kernel acting directly on this original agent itself. And we've considered that in
But
some of our
W is
papers.
only conscious monads connected to each other.
Yeah.
It's not like there is no physical world outside of in
No.
this assumption.
We want to
It's
see it.
compatible with the
Yeah.
possibility of that.
Right.
You concentrate on the
That's right. If there is a physical world, it has to be on your interface. You know, so it has to be described. The physics is the dynamics on an interface. And I mean, it's a direct result of the assumptions that we're making.
because if you kind of propagate what you said earlier on fitness to this framework that you introduce by saying, hey, here there are different postulates, but it seems to me that when you introduce evolution fitness, W was potentially an actual
Yes.
objective world.
Yes.
And at some point in your talk, you introduce this
Yes.
framework, W was not anymore.
No, not
Yeah.
anymore.
I think
But
W
could
is
it be included in it? No, so how do we make it compatible with fitness theory?
Okay, so the idea behind the fitness beats truth theorem was that was a reductio ad absurdum. And the idea there was that if you assume that there is an objective world and you assume that there is a way to have veridical perceptions of that world, given those assumptions itself, there's some kind of a contradiction that's coming up. And the contradiction is that veridicality gets dominated by interfaces of any various kinds,
Right. But
which may be seeing something completely different from
right,
what's
but
in the
The
world.
model interface still has, even if it's very indirect, anchoring
Mhm.
into W as the
yeah,
objective
no,
world.
because W is the state space, is the representation space,
Yeah.
it's not the true space.
Yeah, I mean,
Is the space of the agent that he uses
this
to.
is,
Yeah.
no, W is exterior to the, in a sense, W is not something that the agent itself can actually see, completely. It only sees it through the P kernel.
Yeah, but the fact that there is a W means that it's encoded. It's the same thing than saying
It has a
that
state.
but it's the same thing than saying the
With
agent
people
here.
encoding.
The agent here is represented by the kernel that relates a perception to the world. So this is what allows you to compute let's say what it sees, because of a given observation, it sees only the fiber, like
Yes.
of this. But it means that in this kernel, if it's hardwired, like the biologically, or I don't know, this kernel contains already the world, because it's a function, it's a stochastic function that inputs
Yes.
observations
Okay.
and outputs something. But
Yeah,
then it
okay.
needs to exist W in some sense.
If you say that the agent sees the world, I disagree. But if it contains the world, yes, in some sense, it is related to the world. Yeah.
But so why do you call
So-
it interface? Because for the interface, what you mean is like all the possibilities to disambiguous the observation is all the content of observation, right? Is this line, is this fiber that you get? One observation is going to disintegrate your measure. It's going to bring back your measure to f minus x, or to like all the world states that corresponds to x, and that's why this is the interface. The interface is the.
Well, I mean, mathematically, the fiber is the set of fibers is 1-to-1 with the points in X.
What is the interface?
But you don't. The interface is X.
Okay.
The interface is just X, and X is the set of all conceivable qualia this agent can have.
So is it the same thing? Okay, I see.
It's basically to be able to say formally that this button that I see may not have actually at all in the real world, that I have no access to the shape of the button, may not exist in 3 dimensions. It's because it's useful to me as an evolved species, as an individual, whatever it is. I'm set up so that my interaction with this physical object make it look like a 3-dimensional object. But it might not be actually. Think about, in physics, those exotic theory about holograms, that in fact the universe would be 2D, and your experience of 3D would be an hologram of sorts, as physicists would believe that. So that's the way I was trying to find an analogy. Think about a theory in physics in which 3D space doesn't exist, but is kind of some sort of projection.
Right.
Here, that's the point.
Yeah, in fact,
but the interface may be completely different in terms of the way things appear in it from whatever it is in the real world. Like maybe it's 2D and we see it in 3D or whatever. And in that sense, it's an interface because that's the way we build perception of the world in order to be able to act in it and being fit in it.
Yes.
It doesn't require that there is a structural one-to-one mapping between the shape of that button in the objective world and the way I perceive. But then you move even further, because at the second part of your talk, you even abandon the assumption that there may be the objective external world, for instance, in an holographic theory, a 2D world that is.
Well, that's an excellent analogy, the holography question.
So, but
in
here,
fact,
then your W there is no need, in fact, because now your W is only made of conscious agents.
Yes.
Who themselves do not require that to have a connection with the W to some fiber or some transfer function that would be objective. W doesn't include the W that you had before, correct?
No, that's a good point. The W we had before was assuming some kind of a, well, I think this would apply even here. In this context, in the context of conscious agent theory, a single agent has perceptions which are not veridical of the W it's in. Even if that W was some physical world that as we claim it is, or if it was some other world, whatever world it is, even if it was a world of other agents. So even if W represents the state of the world of all the other agents, including myself,
Could it be compatible that then I'm in the dream of another consciousness? The character, the W is the, I mean, in that.
You know that now you bring up the question of I, which is a.
Yeah, I mean, what I mean is that can we, in that condition, this connect to Kant's remark about non-well-foundedness,
Mhm.
W could perfectly, is it compatible with basically conscious agents being parts of another conscious agent?
There's definitely a hierarchical structure that you could develop of conscious agents
So it's
being
well
put together, or you could decompose a conscious agent into other conscious agents.
Maybe I'm the other conscious agents, I'm actually part of the consciousness of another agent that
But look,
I don't see.
I think that's quite possible.
But
In
that's
fact,
compatible with your formalism? That's what I'm asking.
At the moment, it seems to be, yes.
but look, there's some determinate fact about how many conscious agents there are.
Mhm.
Like if you're a classical Vedantist, you think there's just one. If you're Leibniz, you think there are infinitely many, right? But there's some determinate fact about it that is compatible with the model. So that means that's an objective determinate fact that, you know, you don't have access to in terms of the model,
Yeah,
right? Isn't that right? I mean, the number of conscious agents doesn't follow from the model.
No, it
But
doesn't.
they don't have to
That's
be
an
separate.
outside view, yes.
Yeah. So there is some sense of an objective fact, nonetheless. It's not as if you're saying that we make up the facts about reality.
No. Yes, I mean, no, yes.
Yeah.
Yes. We don't make up the facts,
And but given that whatever the number is, it probably has no bearing on fitness at all. Like, you know, Leibniz could, you know, walk around and navigate his phenomenal world as well as, you know, a Vedantist, right? So it kind of makes no difference. So really, given what you've said about fitness and truth, you should probably just be completely agnostic about how many conscious agents there are.
be agnostic about.
About how many conscious agents there
Yeah,
are.
I'm not making any claims about
So
that.
there is
But how many?
are you going to invoke?
So it could be one.
In fact, there's good reason to think that there could be one,
I mean, it could be only one, is what I mean.
only one, and in a certain sense, ignorance is what gives you the view of a network of agents interacting with each other.
So sorry for this.
Yeah, Vedanta, basically.
Yeah, I didn't want to quite say that here, but I did mention
okay.
Vedanta, so here we go. So, yeah, okay, that's a very good discussion. I think it clarifies a lot of things. Okay, so we've got a phenomenological dynamics, which is much simpler than what we were talking about before, which in any case is not something that we have access to as individual agents, even if we are individual agents. I mean, so a very quick slide where this is Don Hoffman's list of what any theory of consciousness must explain: qualia, choice, learning, memory, comprehension, mathematical knowledge, combination problem, hard problem. You could talk about decomposition, which I might be talking about a little bit later, and so on. So the only reason I'm bringing this up is that work with okay, what's happening with Chris Fields. We pointed out that C networks, as defined, are computationally universal. So if anything in the previous list could be explained by a Turing machine, then in fact it should be explained by a finite CA network too, just as an observation. Okay, so now I want to mention something which we thought about a long time ago, but now that I've begun to read some of your papers, I'm thinking that this may have very interesting connections with PCM. The idea is invention of space within this conscious agent theory. If a conscious agent's actions form a group, so suppose G is a group, And just last night, I think I saw something in one of your papers which said, suppose a subset of G is a group. It's very interesting. We can pursue that later. So suppose G is a group, and if some subset of the agent's perceptions are tuned to its actions, and I'll explain what I mean by tuned in terms of the group in a moment, then the agent can see the fibers of the world as a geometrical space for that group. Okay. And we talked about this in some earlier papers. The initial proof I wrote there wasn't very good, but in the later one, it's fixed up. So the idea here is that suppose you have a conscious agent and its action space is a group. And that doesn't mean that the actions of that G on the world are group actions. They don't have to be. They're just some actions on the world. But G itself is a group in such a way that it's a symmetry group for the agent's perceptual space. The perceptual space is a group space for G. Then if we write the action of G on X as G dot X in the standard way, then for G, for a given action, little g, and the current world state W, the new world state is A, G, comma W. And if the perceptual channel P and the action channel A are attuned, that is for current percept X and next percept X prime, we have that X prime is G dot X. Suppose we have that kind of process. Then the perception action experiences of this observer will admit G as a group of symmetries acting on the set of fibers of P in the world W.
You still have associativity, right? At the time, when you say it's not a group, you mean it's not invertible, but it doesn't. But the actions of the group on the perceptions is not necessarily invertible, but it's still associative.
What do you mean?
Yeah, it'll certainly be associative.
Because you're always considering the mark of chain underlying it, and so it stays.
Yeah, if you go through the whole process, PA.
But it doesn't mean it's not necessarily invertible. Oh, that's what you mean, that you don't necessarily need a group action.
The relation to what we say itself is that the space of
the action A of G.
I know. I see what he's saying. That in a group action, you need to have the identity leaves things alone, etc., etc.
The way I took it with your remark is that G here is not necessarily a group. In the sense,
G is a group.
G is a group, but it's not necessarily a group of symmetries for.
Slightly different things than what.
So you're saying you're not losing associativity, right? You just reversibility. Just saying that maybe acting in one way, you cannot go backwards through action because you have noise or you have.
Yeah, see, the action kernels themselves will be. I don't know what exactly you would mean by associative in this context, because
you compose them.
Well, you don't compose two actions at one time. So in this process,
you can have if the thing is as it's labeled on G, you can always say AG. I mean, this is the question exactly. Can you imagine some kernels that are not associatives? Like, you act first with G, then you act with G prime. You also have a kernel which corresponds to G prime. The question is, you ask that both have to be equal or they can be incompatible.
In this case, it would be something like AG, comma AG prime W.
Yes.
And is that the same thing as AG G prime W? I don't see why it should be.
You don't think it should be? Okay.
Yeah, I don't think we should. We don't have any reason to assume that. That'll be an interesting.
Again, that depends on the scope of action.
Yeah.
Of your action.
Right.
For instance, what you read in our papers is because we think that a lot of actions for us as agents have to do with displacement. So basically how my center of gravity moves around, so orientation, translation, etc., etc. But not all of them. Or
not all of them.
Like
yes.
So
rotations in space, for example.
Yeah, but here the kind of control of my arms to grab a bottle or to do some fine movement, or whatever action arrive in the peristaltism of my digestive tract, doesn't necessarily fit the general type of group we are talking about in the paper that become relevant to model actions when it's
right.
displacement. But then all the nitty-gritty details of my articulation, of my stomachs and whatever, probably they don't obey the same group. So that's what we say the space of action for an agent is larger than the group on which we are concentrating in
Yes.
a particular model, because that group capture mostly moving around, basically.
And I see no reason why this slide could not just simply say if there is a subset of G which is a group action for X. That'll be absolutely fine. In fact, the subset of G which is a group action for a subset of X. In fact, because you know the agent's qualia, some qualia could be space-based, or you know, describable in terms of their positions in space, for example, and some qualia have nothing to do with that. Emotions, for example.
No,
I mean,
that's a lot of emotion.
colors.
To see that
Colors.
one of
you know.
one of the things why it's like the associativity is kind of important in the system is because because the labeling of the states, so of the phenomena of the perceptions, corresponds in fact to the labeling of the actions, which means that when you start giving a name to things that you see, where does it come from? It could be from a representation of your own actions, and so what is primary is in fact your actions and not the space that you're living, that allows you to report. Like the space allows you to name stuff, right? So, and this naming is completely is ad hoc. It's something that's built. So, what would be the thing that is prior to this? The idea is to try in the PCM to put it on the action, which is if you lose associativity in this case, you kind of lose this this possibility of saying that the percept is to explain where the percepts come from. But if the percepts is primary, then it's not that important.
At this stage, we're not talking about the ontogeny or the phylogeny of the situation. And I know you have looked into that. You talked about active active inference and so on. This is just a sort of a static version of that. Okay, you're right. Okay, so that when this first arose, it was interesting. We thought, let's see that we can see that the observer can see what is called a spatial structure, which basically means that the world is given in the world given by a symmetry group, but it's the agent in some sense, together with the world, that makes things amenable. All right, it's not just the agent, but it's definitely within the agent that has the structure, and the world may not have the structure. The world just has to give amenability to the agent.
Doesn't have to be equivariant with the group.
Right, exactly. Which goes back to his to Gregoire's question. Yeah. Okay. So the observer sees. I think I've said this already. The world may not have this structure. And then I did just go over this very quickly. The next slide, we thought let's take a look at probabilistic structure, because that's the measurability and so forth is fundamental to the way we do science. So suppose X and G are sets with measurable structure, and D is a measurable function. This is a decision kernel that decides on actions. It's a measurable function, a measurable kernel. Actually, saying measurable function is not quite accurate. I should say it's a Markov kernel. Okay. And suppose W is any set. The state space of the world is any set. P is any function from W to X, and A is any function from G to W. N is any counter. Okay, so we've got these things that come in without any structure of their own. And we call this W, X, G, P, D, A, N is a reduced conscious agent. No measurability asserted for these extra pieces. But if you have a certain kind of amenability, which means P induces or pulls back a measurable structure on W, and if A respects this induced structure, then it's a simple fact that if A is measurable with respect to the measure structure of G, and that induced by P, then you have a conscious agent. Then everybody is measurable. Everybody is a Markov kernel. and everything works out fine. So the agent sees a probabilistic structure in the world, even if the world does not have this structure. Okay, so we just move on from there.
Follow well with the demonstration. I follow globally, but really.
Okay.
Let's spend because it's interesting. You know, what time is it? Yeah, we have some time.
Yeah. Yeah, I wanted to.
I think it's important to understand.
Okay. Basically, any kernel P will pull back a measurable structure onto W.
Okay, so you have D as a kernel between two measurable sets X and G, and you use P, which is a function, to pull back on W of a sigma algebra. That's what you're saying? P is a function, right?
Yeah,
Okay,
think of P as a function. Yeah, here
Yeah.
I actually want to think of
Yeah, that's
functions,
good.
not kernels. Yeah.
No problem. Yeah. Okay.
Good. So I think I understand now.
Yeah.
I mean, the conclusion, I understand everything about, but
Good. Yeah, A just has to respect the pullback measure and on W and the measure on G. Measurability, measurable space. Yeah, okay. So our mind-body problem.
Like, sorry, but the A is not necessarily A is not necessarily measurable in this case.
No, but it just has to be measurable with respect to that induced structure.
But that's something you force.
Yeah, if it happens. Well, these are all, you know, what happens if. Yeah, let me.
But if it's commutes, it's a number commutes. Well, that's okay. It's okay.
Yeah, I don't think commutative
No,
A.
because D is a kernel, so it's okay. No,
Yeah.
just
Okay, so that is a highly simplified situation, okay, that we discussed. Okay, so what we're beset with now is a reversed hard problem of consciousness, which is, if this is all true, then how do objects and their physical interactions arise in a material world as satisfying solutions to the fitness landscape of a species, as this was your question also earlier on. Of course, now there's a tremendous amount of work to be done, either to show how this could happen or to falsify it. So how does the arena of physical experience, space and time, emerge? So this brings me to the last part of the talk will be about this, about a project which is to make contact between conscious agent theory and the simplest quote unquote description in our academic consciousness of our natural world, which is particle physics. I claim that particle physics is the easiest of the sciences. What do I mean by that? I mean,
it's a 17th century particle physics.
It's not easy to learn. Let's put it that way. It's in fact is some of the most sophisticated thinking of all the sciences. But what I mean by simplest is that it's the what do particle physicists do? They heavily constrain a situation in a laboratory. They throw out everything else in the world and in our experience, and they focus on a very, very specific and precise kind of situation. So that is much simpler than the whole world. So yeah, I wanted to provoke with this claim, and I think I may have succeeded. Okay, so we'll return to this in part 4. But before we go there, let's ask a very basic physics question that has been asked forever, and I don't think it's been satisfactorily answered yet, which is, what is an observer and what does it observe? Okay, so that brings me to part 3. A couple of quotes, which we found provocative. The famous Professor Wheeler in 1982 said, is the entirety of existence built upon billions of elementary quantum phenomena, those elementary acts of observer participancy. And while I was reading this out, I just realized that the expression billions upon billions was something that Carl Sagan really used to say a lot back in the 70s. So that may have had something to do with Wheeler's statement. Anyway, another statement by Wilczek is that we will need to understand that we have that model of consciousness that corresponds to our experience of everyday life. And then he goes on to say, which is fully based on quantum mechanics, but he says that we'll need this in order to understand quantum mechanics. So I'm not quite sure about what I feel about the remaining part of the statement, but I think he's right that we need to have a model of consciousness that corresponds to our experience of everyday life. And I think we're all in agreement on that. Okay, Chris Fuchs in quantum Bayesianism also has the attitude that wave functions describe an observer's beliefs about objective reality, are not objective in themselves, and this could be, of course, argued. Okay, so in pursuit of this, the idea of trying to understand what observers are, what observation is, and so on, we decided to look at the asymptotic dynamics of the qualia kernel. The qualia kernel, which I introduced before, is the experiential kernel for a single agent. Okay, so to study the asymptotic behavior of this, it maps experiences to experiences, and it describes how an agent's experience evolved. And the asymptotics of this will describe stabilities of that experience. Okay, so if X, we're just going to consider situations which are finite. Suppose X has n elements, which we're calling qualia. This should be qualia, actually. The n qualia Q space is the Markov polytope, which we're defining the Markov polytope of all transition probabilities on X. Okay, so that's it. It's an n squared minus n dimensional manifold. It's a cell complex. It has some very interesting structure that we've been exploring. So for non-periodic Q on a finite state space, the Q to the n will converge as n goes to infinity in the Markov polytope to its stationary distribution. In other words, to a matrix which has the stationary distribution on each row. Okay, that's why I put 2 in quotes. So just as a simple example of this, if you look at M2, the qualia kernels of 2 qualia agents, say the 2 qualia, a red qualia and a green qualia, it's an agent that can see 2 colors, then a typical Markov kernel looks like this. And M2 is the collection of all these agents. We can look at it pictorially. This is the Markov polytope for 2 agents. The green line is what's called the Birkhoff polytope. There's the bistochastic Markov kernels. I see you're smiling because you've used a lot of this stuff yourself. And the red line, I guess it's purple, is the fusion simplex. The arrows describe the dynamics, what happens to these Qs as you multiply them with each other, and they all converge to the fusion simplex, okay, which is a simplex. So they all give the same stationary distribution of red and green experiences, and so you get new colors in that process, and this is a kind of a way in which you can think of fusions of qualia taking place.
Fusion, but that with some sort of attractor dynamics that tends to make them mutually exclusive, correct?
Right.
I understand the fusion simplex. It's basically one on y, if you are 0 on x, you can never really. Oh no, it's at the middle that they converge. So it's not big.
If you're at that place, you're already on the fusion simplex, and you don't go anywhere. Those are stationary, actually.
They are stationary, and if I use your interpretation as red and green, is that you cannot decide whether you are red or green when you're on the fusion simplex?
No, well, depending on where you are on the fusion simplex, you're a convex combination of red and green, actually. A particular.
So it's not like when you say the conditional probability of red given green, it's about the transition in time. It's not about the decision whether this is red or this is green at a given instant. Or is it? So for instance, I see this bottle now being green.
Oh.
But there is a certain conditional probability that in fact I don't see it green, but I see it red.
Well, the
But
next,
that's not for you, it's the next step.
yeah, the next
Yes,
step.
okay,
Yeah, the
because I
next step.
interpreted that in this kind of
And
ambiguity.
right.
But there is no ambiguity here. It's either red or green.
At any given moment,
And
yes.
Okay, that
Yeah.
makes more sense now.
But then once you're on the fusion complex, your average
Yeah,
view
yeah.
will be some mixture of red and green.
What are the vectors here?
Beg pardon?
The vector field, what does it correspond to?
It's q to the n as n
Q,
goes to,
okay.
yeah, as n increases. Yeah. So
No, so wait, I just.
so the fusion simplex, of course, is a lower dimensional thing, right? And it's like if that's where if you're producing an agent that sees what's on the fusion simplex, then you're dramatically dropping down in dimension.
Not understanding. So just one. So if I take a point, it's a stochastic matrix, right? One point in this square. What is the vector associated with points? It's the derivative of putting it of q squared.
Q squared minus q.
Okay, so it's not
Yeah.
q power. It's just the dynamical system. Okay. So
Right.
And X, the probability more? The
Yeah.
probability of being green, for instance?
Yeah, X is the probability of seeing green once you've seen, given that you had red before.
no,
All right.
these are all the stochastic matrices.
Right. And Y is the probability is the other one of changing the color. Each of these are changes of color. Right. Right. So you can go up to another dimension just to see how things, M sub n as n increases becomes incredibly rich. And already at M3, where you have 27 vertices now, you have sort of three different kinds of dynamics that going on. You have a fusion simplex that I've shown over there in gray, and you have many kernels as you're going through the process, the Markov process. The process is approaching this simplex in many cases, but in many other cases, there's periodic behavior. And in many other cases, there is a partial fusion complex also, which has lower ranked matrices.
Yeah.
So it's very interesting, actually, what's going on over here. The point I want to make about this is that this dynamics is rich enough already even with just three different qualia, that you're seeing behavior which gives you the idea that if you let n get large enough, you're going to get all sorts of behavior, maybe behavior that looks like particles. Okay.
It'd be interesting to develop nice visualization.
A generalization.
Visualization.
Oh, visualization of this. Yes. Right. Yeah. No, that would be a very interesting computational problem. Yeah. Okay. So all this has suggested a certain idea. Don really thought about this, that there's something called a trace logic, which could be used to describe observers. Okay, so an observer is an agent, ignorant of the whole state space, but observing the dynamics through windows of attention. Okay, and so we often use the word projection. In this case, this is what we mean by the word projection. It projects the dynamics in some windows of attention. It projects it down. So the first projection of the Q dynamics is the agent observing dynamics through a spatial window. Okay. So suppose you have a Markov chain Q S mu, where Q is the kernel of the chain, S is the state space, and mu is the initial probability measure. It induces on any subset a trace chain. Okay, and the trace chain is basically what you get by observing the chain only when it enters the subset A. You can write down the Markov. It's a Markovian chain. You can prove that, and it's proved in an exercise in a book by a professor from Sorbonne. I forget his name now. Anyway. So the trace chain itself has a Markovian kernel, and it's quite intuitive that over here that you start in A, and then you maybe go away from A a certain number of times, and then you come back to A. The equation itself, I think, is fairly intuitive. And it'll have an initial measure, mu A overline. The overline simply means normalized. And mu A is given by a similar formula applied to mu. Okay, so that's the trace chain. The traces have an interesting property that the trace of a trace is a trace. So if you trace to a subset and then you trace further to another subset, it's the same as if you had traced from the initial superset all the way down to the smaller subset.
It's still a trace, what you mean, it's not the same trace. You say that if you trace from a set to a subset and then you further trace from that subset to another subset, it's still a trace, but doesn't mean it's equal to the entire trace.
Yes, the trace of S on A then traced on B is the same as the trace of S on B.
Okay, and then, sorry, I forgot the and then.
Yeah. So given that, you can actually compare kernels. You can say that one kernel which is supported on the subset A is less than or equal to another kernel supported on the subset S if Q sub A is a trace of Q sub S on A. And then the question is this actually a partial order? And because of the first theorem, it is indeed a partial order. Okay, so it's a partial order on transition probabilities.
Sorry, here inferior or equal means what?
Sorry, what?
Trace, your trace of.
The sign inferior.
It's the definition. Definition of it means that there's a partial order and it's defined by A is trace, QA is trace of QS.
Okay.
Right?
Yeah, Q sub A is the trace kernel of Q sub S. So that's what less than or equal to sub T means. So if that's the case, because if Q sub A is a trace of Q sub S on A, then because the trace of a trace is a trace, you have transitivity. And so you have a partial order on transition probabilities. Okay, oops, what happened? Yeah. So then we also have another theorem that if you have a stationary measure in terms of the asymptotics, you have a stationary measure for Q, and Q sub A is a trace of Q, then the mu sub A that I mentioned before is stationary for Q sub A. All right. So stationarity is preserved. And this is interesting because if you're preserving your stationary measures, your long-term behavior in tracing, then you get a partial order on the entire chain, the Markov chains themselves. Okay, so you can compare chains with each other, and if one chain is therefore a trace of another chain, then and its starting measure and these are both stationary measures, then you have a partial order on those chains.
Can you trace out on something stronger than a set like the partition?
I have thought about that. Would be an interesting way to think about things, because that would get you into understanding coarse graining.
Yeah, exactly.
Yeah.
Exactly.
So right now we haven't thought about that, but I think it's the next thing to think about.
The tracing is you who introduced it, or it was something that already
The idea of trace is
no, in the probabilistic setting, for the Markov kernels. The idea
of a trace logic is something we introduced, yeah.
Okay, but this operation,
But the operation of a trace is,
okay,
like I said, it's an exercise in a book by Reviews.
I see.
Reviews was a professor, I think.
But so it's not known if it extends to more general sets. Like if you have two sets, AB and A joint of B and the complementary, A union B complementary. Like,
That's the question.
Okay. Yeah.
That is a very important question about meets and joins and things like that,
Yeah.
and knots. What else
Yeah.
is in this logic? That is not yet known, and we just
solve it by tomorrow.
good.
It's a
We,
problem you will-
the whole point of giving talks like this is for some smart person to figure it out. So anyway, yeah. The idea of coarse graining is actually doing this kind of a tracing a Markov chain on
Yeah, exactly.
what's it called? Coarse graining Markov chains is
lumping.
okay.
Lumping Markov
So that's
chains.
very well understood in statistics,
But
right?
it's very limited. Like lumping a Markov chain
Mm-hmm.
to continue to get a Markov chain is like it's very restrictive.
I see.
Most of the time
Most of the time you don't get a Markov.
no, and you don't get something that is extraordinary. Like even lumping a kernel implies a lot of constraint on the kernel. But you
Mhm.
have a theorem which is that if you iterate long enough,
Mhm.
then the stationary measure will basically converge towards the push forward of your measure through coarse graining, so it's okay. So if you're like
So asymptotically, it's
there's
okay.
a result on the distance asymptotically, and I think I don't remember well, but I think so. This is that it's
Yeah, I
that it's
did.
okay that it's
I did look at a couple of papers.
but
I think
it's not
statisticians
at time
use.
t, right? It's not
Right.
at time t, and I think one of the essence of this is because time is discrete. If
Mhm.
you go to the continuous setting, things are probably simpler because then you have a the fusion equation, so for
Mhm.
Planck, and then coarse graining makes more sense because it stays local in time,
I see.
whereas
I think I see. I believe statisticians use coarse graining to estimate Markov kernels.
yeah.
Right.
But what they
So-
do is they yeah, exactly. What they do is you have a dynamical system and then you cluster, and then what you're so you can so there's um I have to
Yeah, no, that's fine. We
you
can
have a continuous dynamical system and you want to learn a Markov chain on discrete states, so you can cluster your states and then you can learn a Markov chain. And this Markov chain has good property, but it's not the same thing than lumping the underlying Markov chain.
Okay.
It's basically what you're getting. It's I don't remember. I have to recall, but it's related to
Well,
projecting.
we know that there's something interesting here, because you could also think of this. This is a process of ignoring, essentially, and there's other ways of ignoring. There's ways of looking fuzzily at whatever you're looking at, which would be coarse graining of a certain kind. And it would be of interest to see if an observer could be defined in terms of that. Just haven't got to it yet. Yeah.
Because we still don't have a theory of observer.
Yeah.
We say there is an observer, the way it does is through a window. So what is the actual observer itself?
Yes.
That emerge. Listening to you, and maybe you have.
This is the first attempt. This is just a suggestion. Yeah. Right. So quantum and classical logics.
Yeah, exactly. Sorry. So
Yeah,
the
yeah,
point
okay.
is
He's got it.
Yeah, the point is that exactly, yeah. If you want to coarse grain, what you do is you coarse grain the joint distribution and not the transition.
I
And
see.
that's what you do when you have a statistic, when you have a data set, right? You have a time series, you have a data points, and then you're going to count the number of time that things are going to appear, but that implicitly you don't have a transition, you have the joint distribution, if I'm not mistaken.
Mhm.
And so in this case, you can coarse grain, but what you're really coarse graining is not P y doing x or P x t plus 1 doing xt, but P x t plus 1. In this case, you coarse grain this, and then you look at the conditional. So it means you choose a probability measure, it's okay, you can do
Are
this.
you going to the what's called the space-time chain, which
Yeah,
is extending the state space by throwing in the time parameter also?
I'm just saying, imagine
Because that, yeah.
what I'm saying is that you just take a Markov chain and then choose a reference measure for xt. So just let's say Markov chain is just x0 to x1, it's transition, right? So that's the transition. You choose a reference measure, like a measure, which is, for example, stationary measure for pi. Then you have a joint distribution on x0, x1. then you can force grade because you just apply the push forwards on you just send x0, you bin x0 if x was continuous into a finite state, and then you bin them, and then you're going to get a distribution p x tilde 0 x tilde 1, and then you can look at the conditional expectation with respect to the variable, and that's a new transition from the coarse grain, this discrete states that you have, the ones that you get after coarse graining, and you have a dynamical system on the discrete states. But the thing is, when you do this, in fact, it's not exactly the same thing than lumping, because you choose a reference measure. In lumping, you do not choose a reference measure. You assume that you can
do it for any measure.
Yeah, exactly.
Yeah.
And this is like this is what people do when they learn this. If I'm not mistaken, if I remember well, when you learn from dynamical system, discrete dynamical system from continuous observations, like x is x continuous and t is discrete. In fact you know the joint distribution. So this is the tricky part, which is different from what you're saying, because here you don't have a choice of joint distribution. You don't use mu, right? And you know what you use.
No.
You just use an estimation.
If we know anything, we know what's going to happen asymptotically.
But you do it in a way because you use basically the sum of q of a bar from 0 to t, as if you were doing like the Cesaro sum of the estimation of q of a bar, which is in some way, if q is ergodic, will converge towards mu, stationary mu of a bar, right? So it's more interesting.
Interesting. Oh, we should pursue that. Okay, so yeah, just to point out that this logic hasn't been studied. This is very new. What we do know is that this is not a complemented lattice, for example. But it is locally Boolean. Okay, and it's related to something that was done many years ago by Bennett, Hoffman, and the student Multi, called Lebesgue logic. They called it Lebesgue logic for probabilistic reasoning with applications to perception. I don't know if anyone's aware of this. It was published in a journal of mathematical psychology, and I don't know how often people have seen it, but it was a very interesting idea, and it's based on it's a logic on a set of measures on a space. Okay, so. Because of the Lebesgue decomposition theorem, if you have any two measures, you can write them as write one measure in terms of a sum of its absolutely continuous and its singular parts with respect to the other measure. And you can define mu to be less than or equal to nu if mu sub nu, the absolutely continuous part, has the same shape as nu. It's basically nu with multiplied by something. And I'm sure this idea has cropped up in mathematics numerous times, but it wasn't, it has this particular use as a logic of belief, with probabilistic belief. So it turns out that there's a homomorphism from observation to belief, in terms of how we're defining it. Okay, so if Q sub A is less than or equal to Q sub B in the trace logic, if mu sub B is stationary for Q sub B, then its normalized restriction to A, or its restriction to A, is stationary for Q sub A. That's a very nice fact. As a corollary to that, the map from trace logic to Lebesgue logic of extracting stationary measures, at least from that part which has stationary measures, the ergodic part, is a logic homomorphism. Okay, so that's interesting to say that it seems like there's some kind of a logical homomorphism between observations and beliefs, which you would sort of expect to have. Okay, what we have done so far is, of course, the meat. Yeah. No, please.
Homomorphism from belief to observation.
Observation to belief.
Observation.
Yeah. So if
Takes a bit of context.
right. No, I agree. This is there's a lot to say and limited time to say it. It takes time to understand.
We'll do another session wherever you are.
Pardon?
You did another session.
Oh, okay,
Wherever you
of
are.
course, sure,
Doesn't,
sure,
you know,
sure.
you want to go
Thank you.
deep into patterns.
I really appreciate that, yeah,
Right.
okay. So the condition for the meet is fairly straightforward. If you want to have a meet between two elements of the logic, that is very straightforward, but we still have to understand what is meant by join. Okay, and within the sort of the cone underneath a given kernel, you can talk about complements and so on. It's a complemented lattice underneath a given cone, but that's Boolean, so it's not terribly interesting right now. So we'd like to explore the sublogic structure of trace logic, and in particular, if you can find orthomodular complemented logics, lattices as sublogics, that's great because it makes some connection with quantum theory. And we've often been asked, why don't you simply put quantum into the structure of a conscious agent to begin with? And
See where you're headed.
we have resisted that. Pardon?
I see where you are headed. Maybe I'm wrong, but go ahead, continue.
Okay, so where we're headed now is this is the heavily speculative part now coming. Okay, so
You have around 5 minutes.
Okay.
or How much time do you need? Sorry.
for 5 minutes, I've got 14 slides that I can get through very quickly.
Wait, why don't you give us a heads up in 5 minutes?
Mhm. Yeah, okay.
And
Well,
we'll
my
program another session where you'll take your time to do the
Yeah,
15
sure.
to a
It's
30
okay
minutes.
Sure.
for you and with questions.
I think it's better.
Oh, you'd rather ask questions? Okay.
No, and then
No,
we
no.
ask questions in this session, but we read you another session for.
Oh, yeah.
Yeah,
good
sure,
questions.
give us the gist of the idea now, and
that's
we'll
great.
organize a second session in which you're gonna enter into the details of the speculation.
Sure.
Are you okay with that?
So do what now?
Just the gist.
Just, yeah, I will.
That means that we wanna hear more, so we'll organize another session. Are you okay
yes.
with that?
Yes, I'm
We're
fine.
sorry about this.
No, not at all.
Time limitation because of
I'm
the-
also running into a problem here that I'm not able to get to the next slide.
But maybe that's-
The part 3, which is part 4 actually, which is the physical projection, which is our suggestions about what aspects of this dynamics could correspond to particular aspects of particle physics. So what would be bound particles, what would be confined particles, what would be free particles, would be related to, and
You
I,
have to admit, Adele. I think it's why you just click on admit as you're the host now.
click on admit. Can I find my,
He doesn't have access. Click on the.
should I just go like
it's
that?
gonna-
It's fine, just,
Maybe get out.
Can you get out? Yeah,
You don't see it in the.
Okay, anyway, okay.
it says,
I thought it was-
I can't, there we go. Okay. So very, very quickly, the embodied trace observer is limited by tracing over a subset. It's an ideal observer because it's tracing the entire chain, which is infinite. Okay, a real observer will also be doing sampling on finite count intervals. Okay, so the motivation for the physical projection, very quickly, this is what physicists have discovered, is that proton structure is an artifact of both spatial resolution and temporal resolution. As you decrease your resolution, you see all gluons initially, then you see some quarks appearing, getting denser, and then finally you just see 3 valency quarks. This is very interesting. Do these things actually, what does it mean? That has suggested that spacetime, well, that's something which will justify later what we're going to say. But the motivation for the physical projection is that there are some physicists like Arkani Hamets, Will Witten, Selberg, and so on, who are believing that spacetime is not fundamental, there's something much deeper, and it's really geometry. Very interesting idea, positive geometries, like the amplitude-hadron. Now it's called surfaceology. It's getting more and more sophisticated, and they've been able to apply it outside of string theory, which is great because a lot of people don't believe in string theory. They've now applied it to a very large part of particle physics, but it's a static extension. There's no dynamics. They're these beautiful static objects. Okay. And so what we were thinking is that this Q dynamics might actually give us a dynamical underpinning of these positive geometries. Okay, so you trace on recurrent communicating classes. Okay, you sample over fixed finite intervals of the counter. And what you're going to get is, as a result, is the observation of the chain and its asymptotics. These observations are sampled traces.
So it's ergodic.
Pardon?
The system is ergodic, could we say that?
Yeah, we're only considering those ergodic ones, which.
Yeah, but is it built in? By definition, it's ergodic?
No, there are, so those corner points, they're not ergodic at all. They, so but the majority of kernels will be ergodic. So, I mean, generically, yeah. So, very quickly, this is what we suggest, that if you sample the trace chain and what you're basically is getting is a sampled kernel. And if your kernel looks like this, it's referring to a pair of free particles. If it looks like this, where there are small numbers in the off-diagonal blocks, then you have bound particles which are interacting with each other. If you have a partite set where you have confined particles, this is wild suggestion.
Well, I think that Leibniz would have loved that. You're making a theory of monads for the first time. You can understand how monads can be seen as particles and then how they can interact.
Mm-hmm.
Leibniz, and you can perhaps talk about that.
Maybe we should conclude now.
Yeah,
Okay.
Otherwise they're going to kick us out,
Yeah.
and they are.
Okay.
Please.
So let me zoom through the next few slides. Okay. Mass, zero mass particles like light photons. Particles are described by kernels with zero entropy rate. It's the fastest you can get. Okay. I just wanted to actually show you that. But beyond that, the different resolutions that you get, momentum, energy, position, time, speed, spin, and so forth, all could be described. There's a notion of decorated permutations that comes into the amplitude-hedron. And so our computational experiment is start with a large Markovian matrix with a single communicating class, compute sample trace chains in varying spatial temporal windows, and properties of this transition matrix may correspond to physical properties of particles. And if they do, then it's great. If you can show that there's no comparison with the experiment, then forget it. Then we have to go back to the drawing board. Okay, so
Yeah, the last part was too fast for me, but then.
yeah,
Interesting.
it's speculative and it's sort of it's a stimulating part.
But too fast.
Yeah. So this is the end.
Oh, no.
Excellent. Two more slides. Sorry, but this is just because this is your invitation meant so much to me. That because it's a pilgrimage. This is a place which my grandfather loved. He spoke, I remember a French diplomat in Delhi realized that my grandfather spoke French. He started speaking to him and he said, "This is amazing. You speak like an old Parisian." So I wanted to show you his thesis was published here in Paris in 1917. And his name was Hari Chand. Shastri is a degree in Sanskrit. And but this is the way he felt, which I thought you might like to see.
Nice.
And I really, I'm so grateful to him for his legacy. Yeah. I wanted to point that out. Thank you. Thank you.
So we need to organize another session so that we can also
Sure.
present your stuff, but we can also go deeper in certain discussions.
And honestly, I need to go much deeper into the research for this also.
Because I
So-
can, at least you and Grégoire, I can be a witness. We
Yeah,
can
I-
interact at a level that is really needed.
Oh, yeah.
But at the same time, both
he
of you
can
are
teach me a
capable of
lot,
interacting
actually.
with me.
I could, maybe, you know what, I could maybe try to, it's a pity that you don't stay longer because I could probably find a version of the text in the library of Sorbonne.
Oh, you will? Yeah, I'm sure you
That's
can.
cool.
I have the book also, the
Yeah.
original book. And there's also an appendix that he wrote later, which,
Kini is online. Do you want to say something before we leave?
Thanks.
Well, so we don't have time for discussion. Is that right?
To kick us out like last time, you know, this is French bureaucracy.
so Ken, I mean, we can also, talk later, maybe, if there are a lot of philosophical questions I have.
Yeah, I mean, but what is the plan? We'll have a second session
Another session perhaps later in this month.
I think
later this month. Okay.
Not in Paris, of course.
when you want, whenever you
Yeah,
want.
sure.
Tell me your
Yeah,
best
maybe
moment.
closer to January because, a
Closer to
lot of
January.
things are happening
Yeah,
between
that's
now
right.
and then.
Closer to
After New Year, maybe.
Yeah, after New Year.
Or I see. Before or yeah, maybe after New Year would be better.
Yeah, because they're.
Yeah, my son's school is ending at the end of
Yeah.
this week and we'll be taking him.
Oh, yeah, but
I need him
how
to
about
learn
the-
how to ski and
around the
stuff.
20th of December. The 20th.
Yeah, because you leave also, so it's better if you stay,
Yeah.
right?
Yeah,
No, I mean, it's better if you stay, what I mean for the talk, because you could do it.
No, I can't. I lost you. Oh, can't hear you, Gregor. I can't hear you. You're muted. No, now I can hear you. So what's? I can barely hear you.
You hear me now? Can you hear me now?
Yeah.
Yeah, sorry. I was saying because also David has to leave.
Okay.
I think it's better if we do all the question session all together because we could do it now. We would have just to move somewhere else, but I think it's better that we.
I think we should do it. I've got to go pick up my
I
daughter.
can't hear. I can't hear you.
I can barely. I have to go too.
Okay. You hear me now? Can you hear me now? Okay, cool.
you could ask the same
Okay.
questions
Thanks a lot.
on
Oh,
Zoom.
okay. Let me know. Okay.
But,
Bye-bye.
because we give time. This is important.